All right. Great. It's great to be back. It's great to see you back again here today in CE 347, Urban Stormwater. I got an exciting lecture for you today. A couple of quick announcements before we get started. Homework 1 was posted. This is due tentatively next Thursday. So expect for it to be due next Thursday. If we don't get through all the material in time, I can extend that potentially, but just for now, assume that it's going to be due next Thursday. Okay, and that's going to cover primarily our material on open channel flow, which we'll be covering over the next 3 or so lectures. Okay. In other news, Becky's office hours have been posted. So Becky is going to be hosting office hours Monday and Wednesday at 2 p.m. to 3 p.m. So please come see Becky if you have questions on the homework. My office hours, again, are today and Thursday from 5:30 to 6:30. Okay. Finally, the group formation poll has been posted. Okay, so this is the poll that's going to be used to determine your project groups for the semester project. It'll ask you some information, namely, what other group members you'd like to work with, what group members you might not want to work with, as well as your experience level with the software that we're going to be using in this class so that we can help develop kind of even groups, okay? So that's due Friday, but if you can get that to me sooner, I think that would help in the formation of the groups. So try to get that into Canvas as soon as possible, okay? Great. I should also note on Canvas, I'm posting recordings to the lectures under pages, so you can find them under Zoom recording links, okay? And I have lecture 1 on open channel flow posted there for you, okay? If you also haven't found it yet, the homework is under homework assignments here, homework 1, and you submit homework through Gradescope, which can also be found through Canvas, okay? Great. Are there any questions on course logistics before I move on? Any questions? Oh, also, remember that I gave you an opportunity for extra credit in the last class. I asked, one student asked about the dH by dx term in the Saint-Venant equations, and if you can figure out why the centroid height disappeared, and send me an email or just a document describing why, I will give you extra credit point for that, okay? Great. Are there any other questions before we move on? Awesome. Okay. So today, I have a pretty packed schedule for you. First, I want to review the open channel flow equations that we covered last time. I'm going to focus in on uniform flow in particular today, because that's going to be important for the design work we'll be pursuing later on in the semester. I'm going to give you an opportunity to do some examples in class on uniform flow equations. And finally, we're going to talk about the energy equation. Okay. Great. So let's go ahead and review what we talked about last time. So last time we derived the most general equations for flow in open channels, okay? We derived the Saint-Venant equations. These equations essentially describe the flow dynamics within open channels in pretty much any case you can think of, varying both in time and in space. And it consists of 2 equations. The first is the continuity equation. And this is essentially a mass balance. And we showed that for open channel flow, the flow at any point in the channel has to obey a mass balance at every point in time. The other equation is the momentum equation. And this is a force balance. Oh, running out of space here. Okay, I can't write that far on the screen. I'll just write, this is momentum. And this is essentially Newton's second law, F equals ma, applied to a volume of water, applied to a control volume. So let's go through the different terms in these equations and just kind of recall what they each mean. Okay. So this term here, dA by dt, this is essentially representing the change in mass within our control volume. This dq by dx term here, this represents the mass flux through our control volume. And this term QL here represents the lateral overflow into the channel. Okay. So this equation here is essentially just saying that the change in mass within our control volume in the open channel has to equal the mass in minus the mass out. Okay. The other equation was our momentum equation. This one was a bit more complicated, but it's essentially just applying Newton's second law to our control volume within the open channel. Okay, so these first two terms have to do with our change in momentum for our control volume. The first term, this dq by dt, this represents the rate of change of momentum within our control volume. The second term here, this is probably the most hard to think about of the terms in this equation, but this represents the momentum flux through our control volume. Okay, so in other words, the momentum out minus the momentum in. And the rest of these terms here describe the sum of forces acting on our control volume. Okay, so they represent the three primary forces acting on our fluid control volume. The first term here represents the hydrostatic force. Okay, so this is the pressure force exerted by the water on either side of our control volume. The second term here represents our gravitational force. Okay, so that's the weight of the water itself. And this final term here represents the frictional force. Okay, so this is the force exerted by friction at the bottom of the channel. Okay, and this is essentially the most general form that you can derive to represent fluid flow in an open channel. Note that this is one-dimensional fluid flow. These equations themselves are a simplification of the equations for 2D flow in a channel, which are called the shallow water equations. And those equations are themselves simplifications of the full 3D equations for dynamic fluid flow, which are the Navier-Stokes equations. So this is a simplification, but for 1D open channel flow, this is about as complex as you can get. And this represents the full dynamics of flow, essentially in any case that you can think of. So these equations are not just theoretically important, but they're also used in numerical solvers, okay? So the Saint-Venant equations are used in SWIM, EPA Stormwater Management Model. Essentially, these equations are solved in discretized form to simulate the flow within a channel network, okay? They're also used in the dynamic form of the Heck-Rast solver. Okay. Great. So they look pretty complicated, right? And they were somewhat complicated to derive, but ultimately it's not a mystery. The Saint-Venant equations that describe the full dynamics of fluid flow in open channels is really just an outcome of applying conservation of mass and F equals MA to a control volume of water. And that's what I want you to take home from last lecture, okay? Can all be derived from first principles. Okay. Now, the Saint-Venant equations themselves are somewhat difficult to solve. So in practice, we often use simplified forms of the Saint-Venant equations, particularly if it's not necessary to solve the full equations for unsteady flow. And I gave you a couple different examples of reduced order dynamic models. The first was the diffusive wave, okay? And does anyone remember how the diffusive wave was derived? Essentially, it's the same as the Saint-Venant equations, but we just assume that the system is in static equilibrium. In other words, we assume that these momentum change terms go to zero, okay? So for the diffusive wave formulation, we assume system is in static equilibrium. And do you remember what we lost the ability to represent by making that assumption? Does anyone remember? Yes. Right. So we can't model flows that are kind of dominated by inertial effects. We can't model flows that have a lot of momentum. So I gave you an example of, right, let's say we have kind of this parabolic channel here. We have water shooting into it from above. And the water, if you think about it kind of intuitively, what would happen is that the water would run through the channel and then shoot out over the top. Okay, the diffusive wave can't represent that kind of flow, okay, because we've removed those momentum, those dynamic momentum terms from the Saint-Venant equations, okay? But in practice, it tends to be very good at representing the kind of flows you might see in large river systems. Okay, so what it will look like when you simulate the diffusive wave equations is, let's say you have a channel. And you'll start off with some wave entering the top of the channel. And then that wave will kind of move forward in time. And as it moves, it will spread out. And the peak of the wave will also kind of get steeper. And if you've ever gone to the beach and you've looked at waves moving on the beach, you can kind of see this, right? The waves kind of spread out, but they also get steeper in the front. Okay. And this is why it's called the diffusive wave, because the wave is kind of spreading out as it moves forward. It's kind of diffusing in space. Okay. Now, the second simplification we gave for the Saint-Venant equations is the kinematic wave. Okay. Does anyone remember what else we removed to create the kinematic wave approximation? What force did we remove? Yes?
The hydrostatic.
Right. So in this case, we're going to ignore the hydrostatic force. Okay. So in other words, we're going to consider only friction and gravity. Now, what do we lose the ability to do when we consider only friction and gravity forces acting on the fluid? What can't the water do? Yes? Sorry? Right, so it can't model backwater. More generally, though, what can't the water do if only frictional and gravitational forces are acting on it? Yes?
It can model like change in depth.
So it can still model change in depth. Right, if we have an open channel and we have only friction and gravity acting on our control volume, okay, so we have gravity, which is a component going in this direction. And we also have friction, which kind of counteracts gravity. There's no force that can push the water uphill. Okay, so water can't move uphill in the kinematic wave formulation. I'll just write that down for you. Note, water can't move uphill. And as a consequence of that fact, we can't represent backwater effects, okay, in which an obstruction downstream influences the water upstream. Okay, so in terms of what it'll look like, the kinematic wave looks a lot like the diffusive wave, except that it essentially removes kind of the diffusion aspects of this wave. Okay, so you'll have a wave moving in from upstream. As it moves downstream, that wave will get steeper. But unlike the diffusive wave, it won't spread out. Okay, it'll just get steeper and steeper. Okay. Great. Are there any questions on these reduced order formulations of the dynamic wave equation? Okay, so I will note kinematic wave. This is used in swim. It's used in HEC HMS. It's also used a lot to represent overland flow, as we'll see later in class, because for overland flow, often the hydrostatic and inertial components of the force balance don't really matter that much. The diffusive wave, a further simplification of the diffusive wave is used in HEC HMS. Note that this is called, it's called the Muskingum-Kunge method. Okay. All right. Give you a second to write that down. Okay. All right. And last time at the very end of class, we talked about static simplifications of the Saint-Venant equations, okay? And essentially this is for the case where the dynamics are not varying in time, okay? So essentially the fluid flow stays constant within a given channel reach. Okay, so there are two cases we looked at last time. The first is gradually varied flow. Okay, and so this is steady state. In other words, all of the time derivatives are equal to 0. Okay. And you encountered gradually varied flow in hydraulics, but essentially what gradually varied flow allows you to represent are the cases where the depth and flow aren't changing with time, but they do change with space along the open channel. So one type of gradually varied flow you may have encountered is backwater effects. Okay. You have flow in an open channel, something is downstream is causing the water to back up, and you end up with this gradually varied flow profile that stays constant in time, but it changes over our spatial coordinate. Okay, and at the very end of class, we showed you essentially the furthest simplification we can make to the full dynamic equations of flow, and that is the case of uniform flow. So like gradually varied flow, it's steady state. In other words, all of the time derivatives are equal to 0. It's also at static equilibrium, so the sum of forces is equal to 0. And we make the further simplification that the friction force balances gravity. Okay. And that's what I'm going to talk about for most of the lecture today. Essentially, for this case, the only situation you can get is a water surface running parallel to the bottom surface of the channel. Okay. Why is that? Well, the flow we know can't be varying in time, right? It's also in static equilibrium. And finally, the hydrostatic force is balanced on both sides, right? So we have to have equal pressure force on both sides. Which means that the water surface has to be parallel to the bottom. Okay. And for today's lecture, we'll be examining this case in more detail because uniform flow is ubiquitous within stormwater design, okay? Because it happens to be one of the few cases that we can actually solve by hand, okay? Great. Are there any questions before I move on? Any questions about uniform flow? Okay, cool. So let's move on. And I actually want to backtrack a little bit. And I want to, again, derive where this uniform flow equation comes from. Okay, like every other equation we're going to be dealing with in this section of the course, it can be derived from the Saint-Venant equations. So let me just go ahead and do that again to refresh your memory. From the Saint-Venant equations, we have dA by dt plus dq by dx is equal to the lateral overflow. That's the continuity equation. For the momentum equation, we have dq by dt plus dqu by dx plus ga times dh dx minus the bottom slope plus the friction slope is equal to 0. Okay, so for uniform flow, let's just recap. We assume that the system is at steady state, so all the time derivatives go to 0. Okay. We assume that the lateral overflow into the channel is 0, which also means that dq by dx has to equal 0. We assume that the system is in static equilibrium. So this term goes away because the sum of the forces is equal to 0. And finally, we assume that the hydrostatic force is balanced on both sides. So this dH dx term goes to 0. And what we end up with is the expression that the channel bottom slope is equal to the friction slope. Okay. This is the equation for uniform flow. What I'm going to do next is I'm going to use this equation to derive an equation that you may be more familiar with that allows us to express the discharge for uniform flow conditions. Okay? Great. Are there any questions on this derivation before I move on? Okay, cool. One quick question. What is the friction slope? Does anyone remember from hydraulics what the friction slope is? So it's the slope of the energy grade line. Remember? Okay, so the friction slope, this is the slope of the energy grade line. Okay. So what is the energy grade line? Does anyone remember? Yeah, so the energy grade line is equal to the channel bottom elevation plus the depth plus the component of the energy due to essentially the kinetic energy. So this would be velocity squared over 2g. Okay. Also from hydraulics, you may remember the hydraulic grade line. Okay, does anyone remember what the hydraulic grade line was? Yeah, so it's just the elevation plus the depth. Okay. Okay, so the friction slope is the slope of the energy grade line. Okay. Note that the energy grade line, the slope of the energy grade line is not the same as the slope of the water surface. The slope of the water surface is dH by dx. Okay. So that's a common misconception that I just wanted to address. Okay. So if you remember from the last lecture, when we were deriving the Saint-Venant equations, we gave the following expression for the friction slope. Okay, we showed that the friction slope was equal to the mean shear stress times the wetted perimeter divided by the acceleration due to gravity, g, times the cross-sectional area times the density. Okay. Now, what I want to do here is I want to rearrange this equation to isolate the mean shear stress on the left-hand side. So we can do that by multiplying and dividing through by these different variables. And what we get is that the mean shear stress is equal to G times the density of water times A over P times the friction slope. Does anyone recognize this term here? Yeah, what is A over P? Can someone shout it out? Right, A over P is a special term. This is called R, which is our hydraulic radius. This will appear in a lot of equations that we'll be using in this class. Okay, so we can rewrite this equation here in terms of R instead of this A over P term. What we get is tau naught, our mean shear stress, is equal to G times rho times R, or hydraulic radius, times the friction slope. Okay. Now recall, for uniform flow, the friction slope is exactly equal to the bottom slope. So we can substitute that in for our expression for the shear stress. Okay, we have that our shear stress acting on the bottom of the channel is equal to G, the acceleration due to gravity, times rho, the density, times R, times our channel bottom slope, S naught. Okay, note that this equation only applies for the case of uniform flow. This is not true in general. Okay, but we now have an expression for the mean shear stress acting on the fluid body. Okay, to derive an equation that'll give us the discharge in the open channel, what we need to do is we need to find another equation for our mean shear stress and equate that to the current expression we have here. Okay, and one such expression is obtained through Newton's drag law. Okay, so you might remember this from physics. We have for an object, the shear stress, the mean shear stress is equal to a resistance coefficient, CF, times the density of the fluid, times the velocity squared over 2. And so this is Newton's drag equation. And what we can do is we can take this equation for the mean shear stress and equate it to the other expression we just derived. And what we get is our resistance coefficient times the density times U squared over 2 is equal to G times rho times the hydraulic radius times the bed slope. Okay, now what I'm going to do is, oh, sorry, you have a question? So U is velocity. Okay, U is the velocity. I'll usually use U for the velocity instead of V, just to avoid some confusion with other terms that we'll be using later. Okay, so in this case, U is the velocity. I'll just say it's in meters per second. Okay, so what I'm going to do now is I'm going to isolate on the left-hand side for our velocity. Okay, so let's just rearrange here. And what we get is that the velocity of the fluid, we rearrange this, we will get square root of 2g over our resistance coefficient times the square root of the hydraulic radius times the bed slope. This term right here, this is essentially a constant. So let's just call this C. And what we end up with is the following equation. We have that the velocity of the fluid in our open channel is equal to C times the square root of the hydraulic radius times the bed slope. Okay. Does this look familiar to anybody? Sorry? Yeah. So this equation here, this was originally derived by Antoine de Chezy. This is called the Chezy equation. It's related to the Hazen-Williams equation. And this was derived all the way back in 1768. Okay, so this has been known for a while. But it essentially relates the velocity of fluid flow in an open channel that is subject to gravitational and frictional forces. Okay. The tricky part here is this C coefficient here. Okay, this is difficult to compute analytically. One expression for C was given by Robert Manning. Okay, and what Robert Manning did back in around 1890 is he derived the following expression for that coefficient C, essentially based on a bunch of statistical averages of real world experiments for open channel flow. And he derived the following expression for that C coefficient, phi over n times the hydraulic radius to the 1/6 power. Okay. Where this phi term is essentially a term that depends on which unit system you're using. The R is the hydraulic radius. And this N, does anyone remember what this N is called? Manning's roughness coefficient. Okay. And what you get if you take this equation and you plug it back into Chezy equation, what you get is, let me just write that down. Plugging this value back into Chezy, we get that the velocity of the fluid flow is equal to phi over n times r to the 2/3 power times the channel bottom slope to the 1/2 power. Usually this expression is written in terms of the discharge. So we can just take this expression here, multiply it by the cross-sectional area, and what we get is the following expression. Q is equal to phi over n times the cross-sectional area times the hydraulic radius to the 2/3 power times the channel bottom slope to the 1/2 power. Okay, and this may look familiar to you. This is known as Manning's equation. Okay. So it's usually known as Manning's equation, although in other parts of the world, it's often given a different name. Really, the equation was primarily derived by Chezy. What Manning did was he came up with an expression for this resistance coefficient based on essentially a bunch of empirical studies. So note that this expression here for the resistance coefficient, this really has no physical basis. This is essentially completely empirical. Okay. But nevertheless, Manning's equation is used extensively in the field of hydraulics because it gives us an expression that relates the depth in the channel to the discharge, okay? And it's used for design purposes within the field of open channel flow, essentially because it's really easy to work with and it's often sufficient for the purposes of design. Okay, one quick note I want to make before I move on. This value phi here, so phi depends on the unit system that you're using. Okay, so phi is a coefficient that depends on our unit system. Okay. For SI units, where the discharge is in cubic meters per second, phi will be equal to 1. And for US customary units, where the discharge is in cubic feet per second, phi will be equal to 1.49. Okay, so this is essentially just a consequence of that empirical formulation for the resistance coefficient. The value of phi changes depending on what unit system you're using. So keep that in mind when you are doing homework problems. Always keep in mind what unit system you're using. Okay. Are there any questions on where Manning's equation comes from before we move on? Okay, cool. So what I'm going to do next is I'm going to give you a couple examples using Manning's equation. Like I mentioned, this equation is used extensively in stormwater engineering. We're going to use it a lot in this class. What I'm going to do now is I'm going to give a couple examples of using Manning's equation to solve open channel flow problems. The first example I'm going to do for you. And the second example, I'm going to give you a little time in class to work on it. I'll come around and give you help as needed, okay? Okay, let's do a couple examples. First, let's consider a channel that is 8 feet wide. Actually, let me go back, make a note. It's a rectangular channel. Eight feet wide. It has a bed slope of S naught is equal to 0.0004 feet per feet. And it has a depth of flow of H is equal to 2 feet. Okay. What I want to do is determine the discharge in the channel assuming uniform flow. Okay, and let's let the Manning's roughness coefficient be equal to 0.015. Okay, so this is a pretty straightforward problem. We have the dimensions of the channel, we have the depth of flow, and we need to compute the discharge in the channel, assuming uniform flow conditions. Okay, so we can apply Manning's equation. We have that the discharge Q is equal to phi over N times A cross-sectional area times the hydraulic radius to the 2/3 power times the bed slope to the 1/2 power. Okay. Okay, so first, let's take a look at these terms, A and R, and let's try to express them in terms of our known hydraulic geometry. Okay, so we have a rectangular channel. Let's go and let's try to find the area and the hydraulic radius. Okay, so rewriting this, we have phi over N. Okay, let's say that the width, let's just call it B. So what is the area? What is the cross-sectional area of flow in terms of our known variables here? Right. So it's the channel width times the height. Okay, that's right. Now for R, what is R again? Right, so R is the area over the wetted perimeter. Let me go ahead and actually just draw this channel out for you. This is a rectangular channel. We have a depth of flow of H. And we have a width of B. Okay, so R, we know, is equal to the area over the wetted perimeter. Okay, so the numerator of this equation will just be BH, as we had before. And what is the expression for the wetted perimeter? Can someone raise their hand? Yes. 2H plus B, exactly right. Okay. Okay, so we have R to the 2/3 power, so we raise this to the 2/3 power. And our channel bottom slope is raised to the 1/2 power. Okay, so let's go ahead and plug in our numbers. What's our value for phi? 1.49. Our Manning's roughness is 0.015. In this expression here, we have the width times the height, so that is 8 times 2. And for this here, our numerator is 8 times 2. Our denominator is 2 times 2 plus 8 raised to the 2/3 power. And our channel bottom slope is 0.0004 raised to the 1/2 power. Okay. And if you evaluate this expression, what you get is a discharge of 38.5 cubic feet per second. Right. So that's how you apply Manning's equation to compute the discharge for a given depth. Okay. So that could come in handy for your homework. Next, I want to give you a problem that's a bit more challenging. Oh, sorry. First, are there any questions on how I solved this problem? Great. So next, what I want to do is I want to give you a problem that's a bit more challenging. And I want to give you a chance to work on it on your own or with your neighbors. Okay. So for the channel described in the previous example, determine the depth if the flow rate is 100 cubic feet per second. Okay. And note that this is assuming uniform flow. Okay. So I'm going to give you about 5 to 10 minutes to work on this problem. And I'll walk around and potentially give you some hints. Becky, would you be able to walk around as well? Okay, cool. So I'm going to give you about five or so minutes to work on this problem. And I will check in on you as you're doing it. At the very end, I will reveal the solution, okay? Okay, so I'm just going to write down some of the parameters from the last example so that you have them available. But go ahead and start working by yourselves and with your partners, okay? All right, folks. All right, folks, in the interest of time, let's keep going. Do we have, does someone want to raise their hand and give their guess for the answer? Yes. 3.97. Cool. So yes, that is correct. Answer should be about 3.97 feet. Okay. Right. So let's go through the process for solving this problem. Just because I want to make sure you have this for the homework. There may be some problems on the homework that are a little bit more complicated. What I'm going to do is I'm going to show you how to solve it using a programming language. Okay, so you can solve this problem using a graphing calculator, as many of you have done. You can solve it by hand, as this group has done. I'm going to show you how to use a programming language to solve it, because this semester I want to try to encourage those of you who have an interest in using programming languages applied to the problems in this class. I want to kind of guide you for how you can do that, okay? By the way, who here is interested in kind of learning more about applying programming to the problems in this class? Is anyone interested? Cool, a couple of people. Okay, cool. I'll encourage you to try to use programming in this class. I know many of you, were exposed to programming in computer methods class, and maybe you haven't used it since then. I want to help try to kind of reinforce some of that old material by applying it to the real problems in this class, okay? And this is one example where we can do that. So what I'm going to do is I'm going to actually use a programming language called Python. Who here has heard of Python? Okay, what language is it you learn in computer methods? Okay, so I'm hearing MATLAB, C. Okay, is that right? Did anyone learn Python in computer methods? Okay, a couple of you. I'm just going to use Python in this class. You can use MATLAB to do the same thing. I just find the syntax of Python a little bit easier to understand and explain, so I'm going to do that. So I'm going to use this IPython notebook. So this is kind of just a nice way of displaying code. What we're going to do is we're essentially going to apply a root finding algorithm to find the solution to our problem, okay? So let me go ahead and just run through how we can solve this using a programming language. So the first thing we need to do is we need to import a couple of modules. So I'm first going to import NumPy. This is kind of the core numerical library in Python. And I'm going to import an optimization library called scipy.optimize. Okay, this is the library we're going to use to obtain our root finding algorithm. Okay, the next thing we need to do is we need to define a function. We need to define a function to find the root. Okay, so we're going to essentially try to minimize the difference between our computed value of the discharge and our given value of the discharge, 100 cubic feet per second. Okay, and to do that, we can define a function for the normal flow. Okay, it's going to take the arguments h, which is the depth, phi, which is going to be our unit coefficient, q, which is our real discharge, b, which is equal to the width, the bottom slope, which is equal to 0.0004, and the roughness, which is equal to 0.015. Okay, so I'm going to use Manning's equation to compute the discharge based on the depth along with these parameters. Okay, so I'm going to create a variable called Q computed. So this is the discharge computed from Manning's equation. And I'm just going to enter in Manning's equation here, kind of in the form of code. So I'll have phi times the square root of our bottom slope divided by n, our roughness, times b times h to the 5/3 power divided by b plus 2 times h to the 2/3 power. Okay, so this is just our expression for Manning's equation. And what we're going to do is we're going to try to minimize the difference between our computed discharge and our true discharge of 100. Okay, so what we're going to do is we're going to return Q computed minus Q. And what we're going to try to do is we're going to try to find the root of this function where our computed discharge is equal to our given discharge of 100 cubic feet per second. Okay, so let me just kind of illustrate that for you graphically. I'm importing a plotting library. Okay, and I'm going to define a range of depths. So this is a range of depths from 0 to 10 feet with equal spacing over 1,000 different points. And I'm going to plot the depth versus the output of our function, normal flow, for each of those depths. Okay, so this is what the output of our function will look like. What we want to do is find the point where our function intersects 0. Okay, we want to find the root of this function. And you can see here, it's approximately 3.97, the answer you got. We're going to find that numerically, okay? So to do that, we're going to use the following function, scipy dot optimize dot root scalar. We're going to call it on our normal flow function. We have to pick a method, so a numerical method for finding the root. I'm going to use the bisection method. Does anyone remember the bisection method from computer methods? Okay, no? This is basically the same method your graphic calculator is using, okay? So it's essentially dividing up our search space until it finds the root. And I'm going to bracket it from 0 to 10. Okay, and I just evaluated it. And here's the result. We can see that the computed root is 3.97. Okay, so just like you found from your graphing calculator or by hand for those of you who chose to do so. Okay, yes. Yes, I will post all the code examples in this class so that you can use them for your homework and for your project, right? So that was a way to solve this problem using a programming language. I'm going to continue to do this throughout the semester to kind of give you a little bit of experience programming, and I encourage you to apply programming to your problems on your homework as well. Okay, great. All right, are there any questions before I move on? Okay, so we got about 15 or so minutes left. Any questions? All right. So these two examples that we computed in class, this was using probably the most simple hydraulic geometry that you're going to deal with, which is a rectangular channel. I want to note that the solution procedure will depend on which hydraulic geometry you are using. Now, note that I've posted a link in Canvas under files. So this will be helpful for your homework. Under reference, I posted a PDF document with the area, wetted perimeter, and hydraulic radius for various hydraulic geometries that you will be using for your homework. And I don't think it's loading right now, but just keep in mind that that resource is there for you, okay? Okay, so I wanted to just cover a couple of different hydraulic geometries really quickly. The first and probably most important one that you'll be using is the rectangular geometry. Okay, so if we have a rectangular channel, with a depth h and a bottom width of b, we know that the area, cross-sectional area of flow, is just equal to b times h, and the wetted perimeter is equal to b plus 2h. Okay, so the wetted perimeter being essentially all of the surface that the water is touching. Okay. Another important geometry is the triangular geometry. Okay, so in this case, we have a depth of h. We have a top width of, let's just call it t. And we have side slopes of z horizontal to 1 vertical. Okay, so essentially the slope of the sides is 1 over z. The inverse slope would be z. Okay. In this case, the area can be computed from 1/2 of the base times the height. And that will end up being z times h squared. Okay. The wetted perimeter can be found to be 2 times h times the square root of 1 plus z squared. And the other geometry that you'll be dealing with primarily in this class is the trapezoidal geometry, which you can get simply by adding these two together. Okay? A trapezoid is basically a rectangular section along with a triangular section. If you add those together and take away the wetted perimeter contributed by the sides of the rectangle, you can get the trapezoidal geometry as well. Okay. Great. So one more hydraulic geometry I wanted to talk about, and that is sheet flow, i.e. wide rectangular channel. Okay, so this is a special case that is often convenient to work with. Okay, so let's say we have flow coming down a wide hill or a wide channel. Okay, so we have a channel segment that's very wide, and the depth is small compared to the width of the channel. Okay, so we have a depth of h. We have a bottom width that is very wide. and H is much, much less than B. Okay. So for this case, the cross-sectional area of flow is equal to B times H, right? It's just a rectangular channel, but very wide. For the case where we have the depth much, much less than the width, the perimeter can be approximated as being simply equal to the width B. Okay, and if we have that, we can simplify the expression for Manning's equation. Okay, so we have that Q is equal to phi over N times the cross-sectional area times the hydraulic radius to the 2/3 power times the bottom slope to the 1/2 power. We can separate out the terms of this hydraulic radius. Okay, phi over N times A to the 2/3 over P to the 2/3 times the bottom slope to the 1/2. Okay, and this is equal to phi over N times A to the 5/3 times P to the negative 2/3 times S naught to the 1/2 power. So if we have a wide rectangular channel, note that this can be simplified. So we have A is equal to BH and P is simply equal to B. Okay, so if we substitute those in, what we get is that the discharge is equal to phi over N times the width times the depth to the 5/3 power times the bottom slope to the 1/2 power. Okay. Now, what's nice about this case the case of sheet flow or flow in a wide rectangular channel? Or any guesses? Yes. Right. So you can find the depth in closed form for a given discharge, right? And that's why it's often used, particularly for solvers where this is a good approximation. Okay, so one place where this is used is in SWIM's solver for the overland flow. So this is used a lot in overland flow when you have flow occurring over a wide area. Also, it's used for flow on rooftops because rooftops can be represented as a wide rectangular channel as well. Okay, cool. So let's just quickly summarize. So today we talked about uniform flow. We talked about Manning's equation. What I want to do before I move on is I just want to give you some caveats for the use of Manning's equation, because it's often used in stormwater engineering because it's so convenient to use. It's often used for cases where it isn't really applicable, and you'll see that as we move throughout the course. Sometimes Manning's equation is abused for purposes that it shouldn't really be used for. But I want to just make some notes about when Manning's equation is really applicable, okay? So Manning's equation is only applicable for uniform flow conditions. Okay, it should not be used to represent any kind of time varying flow or flow where you aren't in static equilibrium. Again, this implies that this is only for steady state conditions. Okay, you shouldn't be using Manning's equation if you have some sort of time varying flow. Okay, note that this equation is semi-empirical. So unlike the Saint-Venant equations, which can be derived entirely from physics, Manning's equation does use that empirical term for the resistance coefficient, which means it's not, and not entirely amenable to physics, right? It's partially empirically based. So just important to keep that in mind. So why do we use Manning's equation so much? Namely because it's very convenient to use. Right, you get a one-to-one relationship between the depth and the discharge. And that makes it very important for design applications, particularly in civil engineering. We are often interested only in the peak flow that a stormwater facility might see. We're often only interested in kind of the peak conditions that are experienced at a given stormwater facility. And for that reason, Manning's equation is often used because you can simply apply Manning's equation for the peak flow, for the peak discharge, and you can determine what design you need to handle that peak discharge. Sometimes it's not necessary to model the full dynamical equations of flow if you're only interested in the peak. Okay. And I think I'm basically out of time. Are there any questions before I conclude today? Yes. Sorry, can everybody sit still? I can't hear. Yeah. So I don't know, there are no hard and fast rules that I know of for differentiating between rectangular flow and sheet flow. I will say that sheet flow is often used for overland flow and it's often used for roofs. Okay, and it'll also be a good approximation for streets. Okay, okay. All right, thank you.